Welcome, everyone. My name is David Wood and I chair London Futurists. Before introducing today's speaker, Storrs Hall, I'm going to start by making a confession or an apology. Many times over the years, I have been asked a particular question about futurists, and I have given a reply that I now realize was wrong, and that's why I ought to apologize. My question came in various forms, but went something like this. Futurists can't be trusted. You futurists predicted flying cars, but they're nowhere to be seen. Why should we trust anything else you futurists say? My usual answer to that question has been to try and shrug it off. Serious futurists never made such a prediction, I said. The only people who promised flying cars were irresponsible Hollywood filmmakers or science fiction authors who had other purposes in mind, such as social commentary or entertainment, rather than careful future prognostication. But over the last few weeks, as I read the book authored by today's speaker, I realized that people who had looked forward to flying cars were often very thoughtful, very careful, and very serious in their intent. They truly deserve to be called futurists. What's more, the engineering designs they had in mind were, in broad outline, credible and sensible. What was at fault wasn't their technological vision, nor was it their assessment that flying cars would have strong net positive social benefits. They were correct on that assessment too. So what went wrong? And what else went wrong on what could have been a very positive roadmap towards a future of abundant human flourishing? To give his answers, I'm now going to hand over to Storrs Hall, who is an engineer, a researcher, a pioneer of nanotech, a pilot, and the author of a number of fascinating, provocative books. Josh, you have clearance for liftoff. Take it away.
Why, thank you very much. Okay, well, hello everyone, and I will now hit the appropriate buttons to share my screen. And you should be seeing a few flying cars here. And
indeed, yes.
And now you should be seeing the presentation.
Good.
Okay, so to begin the talk and the first slide and so forth, what you see here is some predictions from the 1950s about flying cars. The one on the left is from an advertisement from the Association of Electric Companies. And presumably this was an electric flying car that we don't quite understand how it would work, but I really wish it would. On the top on the other side is the cover of a Popular Mechanics magazine with a design that they actually got from Hiller helicopters. And then of course we have Tom Swift and his Triphibian atomic car, which was my, not that one book, but all of the Tom Swift books were my major diet of reading when I was of the appropriate age, which would have been down in the 50s. So, and then right at the beginning of the 60s, in 1962, to be precise, we had the Jetsons. And the Jetsons were a tour de force. I mean, every one of these pictures, except perhaps the cover one, is from the first episode. And the first episode is a tour de force takeoff on the Popular Mechanics version of the future. So George Jetson goes to work and he sits in front of this giant console and puts his feet up, and Jane exercises in front of this Jacqueline character where she's exercising her fingers for button pushing, and then she makes breakfast by pushing buttons on the thing called the Futurists, and even that's too much for her, so she gets a robot, and the robot goes to set the table by pushing a button. So anyway, this is the Jetsons was a takeoff, but it was a takeoff of a future that was already well into the zeitgeist by the sort of stuff that you saw in the previous slide throughout the 1950s. To a certain extent, the Jetsons wasn't really about the future, it was about the past. In the past 50 years, the amount of technological innovation that affected the ordinary person was more than anybody had ever seen before in a 50-year period. In fact, only rivaled by the Industrial Revolution of the previous 100 or so years. But airplanes went from the Wright Model B to the 727. I mean, this is a huge difference in air travel. Every family went from basically once seeing a car some rich person owned to having one in the 1960s. They got electric lights and telephones and washing machines and refrigerators and televisions. Up in the city sprang skyscrapers and helicopters. This was a remarkably vigorous time of technological progress that affected everybody in a big way. And what the Jetsons said was, okay, if this is what the past 50 years was like, imagine what the next 50 years is going to be like. Okay, without being a takeoff on the concepts, we can look at a somewhat more level-headed prediction of the future from the 1950s. And if you look carefully at this house and all the cool things they have, it doesn't look futuristic at all because we have just about all of these. The only one that you probably don't have or don't have something like is the helicopter on the roof. Well, they thought in the 50s and in the 60s that ultimately helicopters were going to take over from ground cars and become everybody's flying car, or maybe something better. Well, it turns out that a helicopter makes a perfectly good flying car. I mean, the technology is obviously there. It has some advantages over an airplane by a long shot. The most obvious one is not needing to be at an airport. My airplane takes off my local airport is 100 feet by a mile runway. I could land on one that was a quarter of that size, but this is what the planes that we have now tend to use. That pad, which is in New Zealand, is just 10 by 10 feet. And New Zealand is windy, and look how close it is to the trees. You'd never try and land that close to trees in an airplane. So a helicopter is actually a very good flying machine. That one, which is the Robinson 22, is same number of passengers, same freight load, service ceiling, cruise speed, handles the wind better, which is what you need in New Zealand, than my airplane. So the question is, why don't we all have these or something like them? We have, starting in the 1930s, there have been a long sequence of innovations and attempts at flying cars of various kinds, most of which could have been developed into something usable as a flying car. So what actually happened was we don't have them, and although we could, I mean, technologically there they are. The Jetsons, to that extent, is not a prediction that flying cars were possible. It was a prediction that every working family could afford one. This was actually already happened. That's happened in the turn of the century. H.G. Wells, in his book Anticipations, which is a piece of futurism about the 20th century, describes what a car would be like to a very good extent, but fails to realize that every Tom, Dick, and Harry would actually be able to afford one. Okay, so the bottom line for that segment is that we did have the technology for flying cars, but economics or something didn't work out. Something that people expected in their predictions in the 50s. So here's something economic. This is the title is a book by Tyler Cowen, and the data is from a different book by Peter Turchin, both economists. And it shows you a flat line where wages of unskilled labor had followed a very nice 2% growth curve going back to 1800. And then right in the 1970s, flatlined and has lost contact with the long-term growth rate curve in the meantime. Airplanes had, this is not airplanes as in military airplanes or so forth. This is purely airliners, things that you hire a seat on. But they flatlined starting around 1960, except for the Concorde. The Concorde sort of showed what the technology would have been capable of doing. If you followed that curve up to current date, I could have gotten to London in person in the same amount of time it took us to set the Zoom call up. And if you want to think about whether the technology for that could possibly exist, just imagine getting on a SpaceX rocket and landing on a tail of flame on the other end of your flight, and that would be just about right for the speed. In the United States, right at the end of the 70s, piston engine aircrafts collapsed. And David was talking about how the older airplanes are always seem to have anymore, and he's completely right. This is the private airplane industry collapsed right around 1970 in the United States, and I don't think it has uncollapsed anywhere else. So this is something that the people who were predicting technology along trend lines just didn't foresee. So is that just air travel, or is it everything? The question is, what about all the other predictions that go into the science fiction and the popular mechanics magazine and the people who consider themselves more serious futurists like Herman Kahn? So I went and I took a whole bunch of these predictions from the early 60s and just made a list of them and made a guess as to which ones really happened the way the people expected, which ones kind of didn't make it, and which ones just completely fell flat. And then I plotted those against the amount of energy, the energy intensity that the technology would have needed to become a thing for everybody, say, to have a flying car, or for fusion power to be powering our homes, or there to be nuclear rockets servicing a lunar base, or whatever. So I took all of these predictions from places like Arthur Clarke's Profiles of the Future, also published right in 1962, the same year as the Jetsons. And what did I find? I expected to find a blob that was slightly tilted towards higher energy being less fulfilled and lower energy being more fulfilled, but I was not prepared for the actual shape of the curve. It looked like somebody had kind of filled the page in more or less uniformly and then taken a machete and chopped off the top right half. There's just a hard line of things that didn't happen, and it's very much a function of energy intensity of the technology. Well, it makes sense if you realize that the energy use that people had been using as a historical standard had been growing since basically the 1800s. And this was first noticed and written in terms of a trend by the grandson of United States' second president, whose name was Henry Adams. And he published his autobiography in about 1910. And so the blue line is the energy that he had seen. And but he posited that it was going to continue along this curve. And so when I took the current figures from the EIA and plotted them, the same growth curve matched very nicely, and I call it the Henry Adams curve because he was the first one to point it out in print. And right around the 70s, where everything else fell apart, that the Henry Adams curve flatlined. So any prediction that got made by people who actually knew what they were talking about, were aware of the historical trends, knew what technology was capable of, et cetera, but didn't realize it was going to collapse in the mid-70s, were going to be wrong, because it did collapse in the 1970s, and we've been energy starved technologically ever since then. So the Henry Adams curve flatline explains most of the failed prediction, particularly flying cars. Now, when I say that, I'm now going to go on a flying car excursion and talk a little about actual flying cars here to back up that point. So here's several different possible types of flying cars. The top two are German and American, respectively. The bottom left, the thing that looks like a airplane car offspring, is actually one of the very few flying cars that is certificated and licensed to drive on the streets and fly. It's in Slovakia, of all places. And the one on the bottom right was actually manufactured by Boeing in the 70s as a commuter vehicle, but did not succeed commercially. So we need to know, among other things, how much would it be worth for you to have a flying car, and therefore why would or wouldn't people buy them? So there's a literature, a scientific literature of travel studies, and the interesting thing when you start reading this is that there's a human universal. People like to travel about an hour a day, or maybe it was 1.1, but it's human universal. The average person, not any particular person, but the average person in all of these societies, whether you're walking barefoot or driving in an air-conditioned car, the average person will travel about 1.1 hours a day. In all of these societies, it's a human universal, and that was a bit surprising, but there's lots of data behind this. So you take all the data and, for example, in a place like the United States, you get enough clustering of the data to draw a nice curve through them, and you get a regularity that you can say, this looks like about the kind of trips that people will make as a function of how long the trip is, how often, or what percentage of the time is that the trip they're going to make. Similarly, you can plot trips. Look, there's a very useful function in Google Maps that will tell you how long it's going to take to drive from point A to B, or you can just log your own trips and see. And it works out that the car does about 40 miles an hour point to point, and with roughly a 10-minute latency that has to do with getting out of your driveway and going through stop signs and getting on a highway and so forth. But that doesn't change. The road system is fractal enough that even though you're going a much longer distance, that 40 mph average as measured point to point holds over all of the distances that I looked at. When we take all of these functions and measurements and so forth and do something interesting, every economist knows that you don't know how much somebody wants something. You can't directly measure their utility function, as the economists call it. But what you can do is look, and when they buy something, they wanted it at least that much. So you can do the same thing, not with money, but with time. So here's the cost in time and the value, also measured in time, of trips of a given length for the average person in the United States, in particular, the average person in the suburban United States in a car. And you get this, roughly 70 to a little longer range of the trips that the average person will take. And what it will do is to tell you how valuable those were given the amount of time you're willing to spend to make those trips. So now we can take all those numbers and plug back in vehicles that do better than 40 miles an hour. The first one obviously is going to be the helicopter that we talked about. Turns out that it's just about twice as valuable as a car in terms of how much you're still only spending 1.1 hours traveling, but now you're able to go to twice as many places in terms of the value as revealed by the car curve. And here's a couple of other designs for a flying car of one type or another. The really interesting one is the cyan one, the aquamarine color. That's a jet car that can do airliner speeds, but you have to drive it to the airport and take off at the airport. So on this chart, it never takes off at all. It's less valuable in the car because you're not going to as many places on this chart as you would have gone in the car. But the reason that is that instead of going 50 miles to places, you're going 500 miles to places. And so the total area under the curve for the jet car is more than 4 times the size of the area under the car curve. It would be 4 times as valuable for you to have a jet car as it would be simply to have an ordinary ground car. Now we can do the same calculation, not just for 3 flying possible designs, but for every possible design. That's the beauty of having a computer. And so if you take all the overhead times up to an hour and all the cruising speeds up to 400, you get a surface that tells you how valuable it would be to have a flying car with those parameters. And for something that was airliner speed that you could take off from your driveway, you wind up being 7 times as valuable as a car. The peak is strongly dependent on the overhead time and the cruising speed, but it does peak. And this does not take account of the money you're paying for the car. It's just the time taken when you drive it. And so there's some obviously lots of work, and I hope economists decide this is a cool thing to look at and do lots of studies of it. But right now, this is a fairly simplistic one, but it says that a flying car should be able to be at least 7 times as valuable as a ground car. There's one other thing we need. Turns out that many people who can manage to ride in cars don't really like to fly in small, light aircraft. If you're flying a Piper Cub, it's like flying a kite from the kite. It's bouncy and people get queasy and so forth. Flying a Bonanza, which is a nice big sturdy private airplane, is quite a bit more like riding in a car, and almost anybody seems to be able to take a trip in a 747. The thing that varies the bumpiness of your ride is the wing loading. That is to say, how susceptible the plane is to being bounced around by air currents and so forth. And the higher the wing loading, the Piper Cub is 6 and the 747 is 140, and the Bonanza is in between. The higher the wing loading, the smoother the ride. And so something we want in our flying car, besides it's being able to take off vertically from your driveway and go airliner speeds, is we want it to have a high wing loading. Well, it turns out that you can get very high wing loading simply by taking the wings off entirely and just using the body as a lift shape. And NASA did this in the 50s and 60s, mostly for research for reentry vehicles from space. But they did, and it turns out that one of these things can be made to fly at just 100 knots. They actually tested them at up to 1,000 knots because they were reentry vehicles. But 100 knots, they did most of the testing at these at Dryden Air Force Base, towing them on a rope but with a souped-up Pontiac, which I always thought was just the coolest thing. But anyway, there they are, and they have the high wing loading you need. You get a very smooth ride in one. The problem is, of course, as an airplane, you don't start at 100 knots. You have to be able to take off. And so you need a long runway and all of that sort of stuff. But since you have to be VTOL anyway to get the big value of your flying car, you make one of these VTOL and use that instead. Well, it turns out you can do that. This is a hobbyist thruster that you can buy. It's about $1,000. It's about the size of your head, but it will raise 50 pounds. You put 20 horsepower of electricity into it, and it will produce 50 pounds of thrust standing still. So you just put enough of those in there to overcome the weight of your vehicle, and it can take off straight up. And it turns out that there's plenty of room for that in a car-sized object, and plenty of room left over to put in the power source, which needs to be up in the neighborhood of a megawatt, and enough thrusters to make it go airline speeds, or you can use some of the ones that you have for lift as a double duty thing. But anyway, you get something that looks surprisingly like the Jetsons car or the lifting bodies or any of these other things. And that's what you want. So we can actually say, here's the design for a flying car that you want, the most valuable design that we have talked about. It's worth at least 7 times as much as your car, and it uses a megawatt of power. Well, guess what? You're way over the cutoff. You should not have expected, if you knew what was going to happen to technology and energy, you should not have expected to be able to have something like that, because it's way over in the forbidden region. So yes, we can say the Henry Adams curve flatline, kill the flying car, period. But that leaves us with the question, what killed the Henry Adams curve? Well, it flatlined just about the time we created the Department of Energy here in the US. That's not the real reason, though. I mean, the Department of Energy was a political epiphenomenon to the real thing that happened, which was a shift in culture. People basically started not liking, not just flying cars, they started not liking cars per se. They were considered part of a bad lifestyle and polluted and blah, blah, blah. So anyway, there was a whole cultural shift that needs to be explained before we can understand why energy flatlined. For example, if you, Bill Gates is a good candidate for the leading person in the world for trying to help people and reduce poverty, blah, blah, blah. He says, quote, if you could pick just one thing to lower the price to reduce poverty, by far you would pick energy. And I think he knows what he's talking about, because I would have said the same thing. But as a corollary, if you could pick just one thing to raise the price off to increase poverty, by far you would pick energy. And so the fact is that this cultural shift, which started in the 60s and flourished in the 70s, basically somehow everybody turned stupid and evil at the same time. And we have to understand how this all happened at the same time, and why people gave up on their understanding that of how good and worthwhile it was for everyone to have energy that had been part of the standard understanding of the world up through the entire Industrial Revolution, and in fact most of the 20th century up to the 60s. Well, first cut at the answer is from The Time Machine by H.G. Wells. And if you read through this, the Eloi are the degenerated remains of humanity who are small and weak and without great energy and so forth. The Securitists set a premium on feebleness, and the Eloi are essentially like children. except that they're also pretty sexually active. But the thing is that when Wells wrote this, he expected to take 100 centuries, not one, for people to degenerate to that point. And of course, people have not degenerated in the sense, the genetic sense that he expected. What's actually happened is something a little more complicated. There's a recognized watershed, about $30,000 income per person, where people quit being mostly interested in making ends meet and tend to become more interested in keeping their friends from eating meat. And basically the things that we considered the necessities of life back before, say, 1950, where everybody worked for a living and so forth, started being taken for granted. And that's the way the Maslow hierarchy of needs works. You get up to a certain point, and the stuff below that point, you just take for granted. And whatever the level you happen to be at is going to consume all your interest and time and so forth. And it seems reasonable to imagine that happened with people, especially in the United States, which is where I know most of the details that I do know. And in the 60s, which turns out to have been right around the appropriate income levels for that observation. And the things that happened in the 60s where people suddenly became interested and keenly desirous of fixing all sorts of things about the world, could very easily be seen as the population, or a large chunk of the population, coming up over this horizon in the hierarchy and suddenly being interested in new kinds of things. So as a working hypothesis for some of the social basis of the collapse of the Henry Adams curve, that's one that I think is a reasonable guess. Here's a little more objective way of looking at it. People over the years, this is a graph from the Google Ngrams, where they track the occurrences of words in books. And there's a bump in here for, in the United States, the Civil War, the World War I, World War II. And what they're doing is measuring the occurrences of the word crisis. Well, it turns out that there must have been a gigantically huge crisis starting around the 60s, only there wasn't. What happened was that people became hysterical, and they started writing about crisis, even though most of the crises were essentially being made up and imagined and so forth. So this is at least one possible objective way of looking at what really was a culture shift and not any actual physical problem happening. In fact, it was the opposite. The people in the part of the curve where crisis keeps getting mentioned the most were among the safest and among the best fed and highly remunerated and so forth that people have ever been. So the upshot of this is that you got a cultural ergophobia, where people are basically hate energy, they dislike it, they're afraid of it. And these particular quotes come from the end of the 80s, when it looked like there was a possibility, this is the cold fusion thing, it looked like there was going to be a possibility of clean, cheap, abundant energy without any pollution and without even, contribution to climate change. And all of a sudden, the wolves came out of the sheep's clothing and started saying, yep, we don't like energy, period. It doesn't matter whether it really was polluting or all the other horrible things we said about it. We just don't like energy, period. And this is at least a window into the zeitgeist of ergophobia that had developed in America and the other Western countries over the 70s and 80s. Okay, so we're going to shift gears here because this is not an Eloi Agonistes thing. This is something that's been around for at least 500 years since Machiavelli said it. He was a student of the classics, so he knew lots of cases of things where this had happened in history before him. So this is another human universal. If you have a society that can be divided into groups, and some of the groups are doing well because of the way things work, and they're generally going to be the ones who are in charge and able to make and enforce laws and so forth. Turns out that they are not going to be greatly in favor of progress, and in particular, not greatly in favor of change, because they're doing well and they don't care if somebody else could do better than they were doing because of some cool new invention that might be threatening to their position. So this is standard. This is part of ordinary human dynamics, and it has been true since Machiavelli wrote it. Perhaps the prime example that happened in the meantime, there have been numerous examples of this, but the prime one, the one that really sticks out in history, was Ignaz Semmelweis in Vienna, the doctor who discovered that the fever in childbearing wards was being caused by doctors who had just gone and dissected cadavers and then went straight and delivered babies. And he worked out an antiseptic solution that he required the doctors to use between dissecting and delivering, and cut down the rate of fever enormously. So for his great discovery and good works, he was fired, he was run out of town, thrown into an insane asylum, and beaten to death by the guards. I mean, this is the Machiavelli effect in a nutshell. It usually is not that immediate or that fierce, but it does happen. And I'm going to tell you at least one other, maybe at least two other cases of it that affect our story here. Okay, back to flying machines and the economics thereof. Personal jets normally, right about now, you can buy one of these for about $3 million. Generally, people who have $3 million to pay for their personal jet hire a pilot rather than flying it themselves, but some people do. And that's about what current technology is capable of. And it has most of the parts that you would need for the flying car of the kind that we were talking about. Well, if you somehow were able to reduce the price of this by 100 times, you'd have something that would be car-like and would be worth your money to buy. Well, so what? So it turns out that that kind of thing has happened. There's a famous case of archaeologists working on the Lendbreen glacier up in, I think, Norway, and they discovered this woolen tunic, and they were flabbergasted because a woolen tunic back in those days was an extremely valuable thing, and it was a huge amount of work was necessary to make a woolen tunic, and they were so surprised that it had apparently just been left there by somebody walking across the glacier. They made a movie, which you can find on YouTube or at the URL I have down the bottom of the slide there. that shows the amount and kind of work that would have been necessary in 300 or any other time since before the Industrial Revolution to make something like that. And it works out to be roughly the equivalent of $15,000 worth of work. Well, of course, now you can get one for $50 off of Amazon. So yes, an Industrial Revolution is capable of knocking down the cost of something by a couple of orders of magnitude. And it does it by, in the case of the Industrial Revolution that we are familiar with, harnessing fuels for power and high precision machinery for engines. And it's just a cool little slice of history to look at what a 20 horsepower engine looked like in 4 succeeding centuries. Well, the second Industrial Revolution, or one that's capable of doing this sort of thing again, or if you want to be a purist, a continuation of the Industrial Revolution, was envisioned by Heinlein in the story whose cover you see there. He was writing under a pen name of Anson MacDonald, but that was a Heinlein story. And then Feynman, who had read that, picked up on it for a famous talk in the supper club of the, I think, Caltech's Physics Club or something of right around the turn of 1960. And then, of course, Eric Drexler, whom the London Futurists have heard in person, took and ran with that. And so we have a reasonably good idea of what we could do if we were to be able to get to nanotechnology and build things with atomic precision and run them at the appropriate speeds. And so one of the things that we did, I mean, Eric and I both actually collaborated on some of these designs. But this is the sort of thing that you can design and analyze with current molecular software. And so we know what kind of machines could be built. And we know some things about what that means. One of them is that, yes, we know the value of having atomically precise machines because we made of them. This is the thing that produces the ATP that powers all the other molecular machines in your cells. But it's an electric motor turning a piece of production machinery that by physical force assembles the ATP molecule. And it does a few hundred per second. It is atomically precise, which is one of the reasons it can work. But it's made out of proteins and operates in solution of salty water and all sorts of other things that are results of the fact that it evolved rather than having been designed. If you do design them and you know all the engineering tricks and so forth that we do know, you can improve that to a few hundred million reactions per second. You can build a machine that does 1 million times as much work in a given unit of time. And this is a much, much more productive machine. And it's the kind of thing that can do the cost and price reductions that we were talking about for the second Industrial Revolution. What that does is it vastly accelerates the growth rate. We have an example of that. It's Moore's Law. And when you look at the ridiculous things I'm about to say, I want you to remember the prices and speeds and sizes and energy use and so forth of computers in 1962 and 2022 and compare. If we can move this kind of advance from the world of bits into the world of atoms, we're looking at a physical industrial revolution that will proceed at roughly Moore's Law growth rates, which 40% per year, which means that once we get nanotechnology 14 years later, you're getting your $3 million flying car for 30,000. Not only that, but with nanotech, a whole bunch of things that were not possible will become possible. Simple example, almost, well, more than half the land in, say, the United States is used for agriculture, either raising plants for us to eat or for cows to eat, and then we eat the cows. It's basically a huge inefficient solar collector driving molecular machines, but we can make the molecular machines directly and power them directly and short circuit this so that you don't need essentially the Earth's biosphere to do the other half of the work that replaces, takes your waste products and turns it back into your inputs. So this could portend a huge change in not only our lifestyle, but the necessities of life. You can live pretty much anywhere you want. Okay, you take your flying car and you stick your house on some mountaintop in the middle of the ocean, no problem. But that's nothing. You can live absolutely anywhere in the solar system with one proviso. And of course, that proviso is energy. We got to figure out how to provide energy for these molecular machines, which will use quite a bit of it. So George Jetson's car just is not going to fold up into a briefcase if it's holding a ton of Jet A aviation fuel. We're not going to settle the solar system by burning fossil fuels in Earth's atmosphere. Not only are there not enough fossil fuels, there's not enough Earth's atmosphere. We got to come up with some other way of getting our energy. So here's a possibility. The amount of energy you get from nuclear processes is typically on the order of 1 million times what you get from chemical processes, and there's a lot of it. If you look at line number 4, a perfectly viable nuclear fuel is nitrogen, which is most of the air. And the output of that is just silicon, sand, and tiny bits. I mean, this is remember, this is the equivalent of a ton of jet fuel. It's half a gram of nitrogen. We don't know how to do most of these yet. And to the ones that we do know, we don't have the machines that actually do them properly or efficiently or so forth. But these are the reactions that are possible according to the physics that we know. And so we need to get on the ball and work out how to extract this energy out of stuff that is so common we're swimming in it. Guess what? Back in the Great Stagnation, nuclear physics stagnated. The interest and the number of PhDs in nuclear physics collapsed. The cost of a nuclear power plant exploded, and a very strange thing happened. This was one of the more interesting historical artifacts ever. It's the first visible piece of matter that was made by transmuting elements. It was done by Seaborg, who won a Nobel Prize for it in the original Manhattan Project, and it's visible. I mean, that's just a lens, and it was some micrograms of the new element, which, because it came from uranium and neptunium, they call plutonium. Of course, they didn't realize, but now plutonium is no longer an element. It's a dwarf element, but that's a joke. The thing is that this had gotten forgotten. It was found in the trash in Berkeley Labs, where it had been originally created, and rescued by somebody who recognized what a historical artifact it was, but it was just going to be dumped in a landfill. And so that means that it's just another indication of how badly we have forgotten everything we used to know, and how badly we quit advancing the knowledge that we used to know in nuclear power. So atomic in this phrase, the second atomic age, is a pun, of course. The atomic technology is nanotech. It works with atoms. It makes things with atoms specifically designed and so forth. But the pun is atomic energy, because that's what we used to call nuclear power. And it turns out that if you put the two together, the nanotech makes a huge difference in how easy it is to discover and explore things at the nuclear scale, as well as to build things and to have machinery that is exposed to large amounts of radiation but keeps working, and tiny accelerators and a whole bunch of other things, including the some of the physics that has been speculated as being the basis of how cold fusion worked. Now, I said I would mention a couple of things about the Machiavelli effect. The crushing of cold fusion was one of them. If you go back and you read all the literature with a balanced view, you'll find that there should have been a lot more attention and a lot more work done on that. And the other one was, of course, nanotech itself. And I was there. I was never a huge cold fusion fan until I realized the way that people had treated nanotech was a clear example of what might well have happened to the people in cold fusion. And so I became a lot less skeptical about the cold fusion research as a result of that. But the bottom line is, again, that you add nanotech to the science and you now have the tools to do things that we might expect to be able to do with nuclear energy, and do it with car-sized engines and that kind of thing. Okay, other new technologies in the predictions of the science fiction writers and futurists of the 50s and 60s, robots. They actually got this one just about right. Robots are pretty much at 100% on my chart, and the descriptions that, say, Isaac Asimov gave of what robots would be like in the early 21st century were pretty much right in line with the reality we have. In fact, I even made a nice prediction. It's in this book, which is only 10 years before the AI boom, but I predicted the AI boom, so you can go back and read that too if you want. But it was nowhere near it at as far a remove as Asimov, so I don't deserve anywhere as much credit. But as a result of the robots and the nanotech and the economic growth rate and so forth, George Jetson, in the year 2062, which is when the Jetsons is set, works 3 hours a day, 3 days a week, makes $1 million a year, and owns a flying car with those robots. But this is not the way we ought to look at it. We shouldn't say, here's Jetson, he doesn't have to do almost anything. We say, here's Jetson, let him work as much as he wants, and he'll get that much more than he would by, just sitting in the chair 3 hours a day. It's not how easy it's going to be to do the kinds of things that we do. It's going to be all the new kinds of things we do. It's like the jet version of the flying car, where you're not making the trips to 50 miles out faster than you do now. It's that you're making trips to 500 miles out and other things like that. So ultimately, we're going to have a technology, if we don't do really stupid things, that will give us complete control of the structure of matter, and that includes not only replacing agriculture, but medicine and most other kinds of internet engineering. Clean, cheap, plentiful energy on a scale we can almost not imagine now. Robots and my fondest hope is that a good understanding of the mechanisms of decision making that go into robots in the human brain is going to at least help to some extent our social decision making be a bit more competent. So we'll have flying cars, we'll have personal spaceships, we'll essentially expand to settle the solar system. There's a quip, a joke in the nanotech world, which says, question, when do we get nanotechnology? Answer, just before we settle the solar system. So anyway, when we do that, when we have these three, this triad of technologies, we settle the solar system, it become a Kardashev level 2 civilization, handling the same amount of energy the sun puts out, preserve the earth as a park, and take our fights outdoors. Okay, that is the end of the prepared talk. Let me get back to this.
That was a real tour de force. Thank you so much,
Thank you.
Josh.
Okay.
One question that's of interest to many people is there are lots of interesting ideas and links in your presentation. If people want to follow some of these links, are they in your book or are they on your website? And what's the best way to get these links and people can check out the references by themselves?
I believe most of them are in the book. I have quite a number of links in the book.
And there's a lot more in the book, of course, than you've had time to dive into now. So there's more there.
Oh, yeah.
So that was a question by Alan Crowley. So to the audience, I encourage you to take the time to put your questions into the Q&A window. Vote for each other's questions if you think there's something you particularly want to hear sooner. PNJ asked a question which was on my mind as well, which was this concept of ergophobia. What is it that leads reasonably sensible people, you would imagine, to be so afraid, not just of cheap, abundant energy, but to be afraid of cheap, clean, abundant energy? So what is the basis for that fear? Is it that somehow they imagine it's going to be nuclear, and even if people say it's safe, it's not safe? Is it that they imagine that such a thing would necessarily be distributed by a strong, powerful, centralized agency, which somehow they fear? Or what else lies behind this concept of ergophobia that you have painted?
I think a large part of it is basically the watershed, the step up, the hierarchy of needs, where they start taking the things we get from energy for granted, and then all they can see is the cost. And the cost may just be the cost of gasoline at the pump. It may be the fact that now everybody else seems to have a car and they're always in your way, or something. But all of the stuff that you can do with a car, or can have delivered to your house by a truck, or fly somewhere in an airplane, are just taken for granted. They say, oh, they don't even bring that into the calculation anymore. And if you do that with any technology, all you're allowing yourself to see is the negatives, and that's all you're going to see.
There's a suggestion in some of the questions that we are driven by some kind of negative self-assessment. Martin Bielicki asks, do you think humans slowed down technological developments because somehow we desired still to be limited? We desired to experience limitations. Somehow people might prefer to be subservient or restricted. Do you share that view, or is there something else in our psychology that leads us to sometimes perverse choices?
Well, I take what I think is a more complex view, and my view is essentially that there are lots of people and they have different takes on these things, and some are more into technology and energy, like I am, and some are more into the other sides of things. And to some extent, it's simply where you can get traction and who listens to you and what benefits that brings to you as a person trying to make their way in the world, or trying to become famous or rich or whatever else it is that you want. And but evolution makes us so that we'll all be different, just in case one of the differences is good. And if some of the differences don't work well, then they don't reproduce. And so that's what you should expect. I mean, there's a basic force for variation in the process, and I would be surprised not to see it. So I think to some extent, what's happened is the situation where the Eloi agonistes are more socially predominant is not due to any of the individual people there being any different from the way people always were. It's just that times are such that they're more successful.
Right. So can I dig into another possible reason, which is also in your book, as to why innovation seems to have slowed down from the 1960s and 1970s onwards? Because after all, Machiavelli effect goes back to the days of Machiavelli.
Indeed.
And we've had a lot of innovation, nevertheless, despite that. So what is it that caused the innovation in some of fields of technology to slow down? We've talked about psychological changes, but I think you also have some views about regulations and centralizations and groupthink, which results from more of the funding decisions going through a few single gate points. Do you want to share some of your views on that as well?
Oh, well, yes, that the bit about regulation is one of the set of things that there was a perfect storm of phenomena like that in the 60s and 70s, which is why you had the whole stagnation come at what appears to have been an identifiable time. But regulation was definitely part of it. The collapse in small personal airplane sales, that was one of my charts, was almost entirely due to liability law. The way the law changed, not because anybody voted for a new law, but somehow or other the courts managed to just reinterpret the laws, and then and I'm not a legal scholar, so I can't say exactly who came what first and who did what, but the upshot was, and you can find this in economic histories, it's not even close to being a problem it's quite accepted. Let's just put it that way. It's quite accepted that this is what happened to the aircraft industry, and it was that if you got drunk, got in your airplane, flew it into somebody's house, then the relatives of the people in the house could sue the manufacturer of the airplane who had made it 40 years before, and under product liability law. And that's just insane, but that's the way it worked, especially in America. I don't really quite know how it is in Britain or other places, but it appears to have taken what was a viable and growing industry in the US and just destroy it.
And what about the rest of the world too? And you said maybe you haven't studied other parts of the world as fully as you would like, but is it the case that China, for example, will be governed by the same set of psychological and social impediments to nanotechnology and atomic energy? Maybe there'll be more innovations from India, South Korea, Japan, or other parts of the world where there's different regimes involved.
Yeah, and basically you mentioned a whole bunch of countries. I'll mention a whole bunch of technologies. Cold fusion, for example, is much more popular a research area in Japan as here. Ordinary nuclear and other high energy projects are a big deal in China more than they are here. I'm not really familiar with India, but I think that they are similar. I do know that China has enough bureaucracy that it gets in their way. And although I think they have a culture that is more forgiving of high-tech projects, or even more enthusiastic, I should say, about high-tech projects, the extent of bureaucracy in the system is still a major drag on progress there. The other countries, you can't tell. I mean, the one that I pointed out is that the only fully licensed, certificated flying car that I know of that you can get and just drive right out on the road and fly is in Slovakia. Who knew?
Yes, who knew? I wouldn't have picked that country. So let's talk about this remarkable phenomenon of the Henry Adams energy curve and its stagnation. Do other researchers draw attention to this as well? I mean, there are many curves that show that something seemed to have changed in the 1970s, namely the divergence of productivity and the median wage. That's often shown, that curve, and people say, oh, it's to do with declining power of unions, or it's to do with automation or some other factors. But what about this analysis that you have of the stop in growth in energy use per capita? Have other writers drawn attention to that as well? What are their views?
If they have, I haven't really seen it. Now, that's not to say that they aren't, because I'm by no means an economist. But if you look at, for example, Tyler Cowen's book, where the phrase "the Great Stagnation" comes from, he looks at a bunch of social and economic possibilities, but I don't recall his saying anything about energy per se. So that's probably the best take from a major economist. He's probably the world's foremost economics blogger, and he's a professor of economics at George Mason. I would have to, before he said nothing, I would have to go back and read the book a little more carefully, but I certainly don't remember his pointing that out as a major factor in the stagnation.
Because once you've drawn attention to it, it seems so important, it seems so pivotal, and it cries out for an analysis. And you've offered various possible causes. Other people might look at other factors as well, and it deserves attention, because surely you're right. If there is abundant clean energy to be had, it's going to make life so much better for everyone. And that gets in the way.
Yeah, well, I really don't understand why people haven't looked at that more. I think that there's a bias among economists to look at economic things and not physics things. And so to some extent, I was running up both sides of those rails at the same time.
So you've pointed out that the second atomic age has been delayed. We didn't do the research into alternative fission reactors. We didn't do as much research into alternative fusion reactors, and the molecular scale manufacturing envisioned in various ways by Richard Feynman, and by Eric Drexler haven't moved forward much. Do you imagine that at some stage the second atomic age is going to gather momentum again and we will move forwards? In which case, when might that happen? I'm asking you to be a futurist here.
Yeah, well, I'm going to have to give you the same answer I got from Ray Kurzweil when I asked him when we get AI, and he says, February 17th, 2029, purely as a joke. But the thing is, a lot of this stuff is there to be taken. And the fact is there has been a lot of progress in nanotech. It has not been focused on using and producing productive machinery the way I think it should have. And back in the day when I was the president of Foresight, and I came up with this scheme of, okay, let's just go and do it the way Feynman said we should. I just couldn't get any traction at all, and I don't understand why. But
maybe we should explain Feynman's suggestion that you start with machinery of a certain scale, which can design equivalent of it, a quarter of the size. And these, the quarter of the size, then with some modifications, could design in turn machinery a quarter of that size. And if you do it enough times, then you get down to nanoscale machinery.
Yeah, well, not so much design, but build.
Yes.
You have to be designing yourself, but it's, yeah, and the thing is that if you're going to build a fully capable nanotechnology, you have to have stuff at all these scales anyway. You have to be able to build medium scale machines because they're medium scale things to be done. Not everything your machinery is going to do is going to be done by putting atom on atom or even molecule on molecule. So the full-fledged technology here is going to have working machines at all of these scales anyway. So why not, start building them, starting with the ones you can build, and then, then the ones they can build, and so forth. The fact is that although a lot too many people, in my view, have been concentrating on just going to the molecular scale and starting there, even though we don't really have the right tools for it. There has been some progress made, and there's been some progress made at the other end as well, where the tools that we do have gotten better and better at smaller and smaller scales. So ultimately, it's a question of whether we do a Manhattan Project for this, or it just shows up in the course of normal technological development, however fast that happens to go. I mean, who would have thought that we'd be doing essentially almost atom by atom construction for our computers now? But we are. I mean, and especially given the push into quantum computing, it's become more and more necessary to be able to build devices that are atomically precise. And even in ordinary electronics, when you're just using field effect transistors and so forth, you're getting to the point where your transistors need to be essentially atomically precise as well. So there's going to be more and more work at the edge of atomic precision and construction as time goes on. And although I said 2029 in jest, I wouldn't be surprised to see something that I would call nanotech then. I also wouldn't be surprised for it to be 10 years later.
So just to recap, the research in the past was held up because it looked like it would be a long-term project. There wouldn't be useful commercial products arising for quite some time. You would need to do several layers of this, but you are arguing that, on the contrary, we are now at the stage when even a relatively short project could build on the technologies that's already here and come up with useful products en route to the complete solution. Have I got that right?
Yeah. Yes. One of the paths into this kind of production at increasingly finer scales and so forth is the 3D printing industry. And there's clear value to being able to print objects with finer and finer precision and of more and different materials and so forth. And that's happening. So I expect one of the major pushes towards what ultimately is going to be what I call nanotech, is going to come from that source.
So there's 3D printing of more varieties and smaller precision. There's quantum computing, which has a huge amount of interest in it these days, understandably. What about nanosurgery? And I hear a lot still from time to time about we're going to have a breakthrough with nanosurgery. Is that something that you would agree with as well, or is that a bit hype?
Well, that actually, surprisingly enough, doing nanosurgery was the reason for producing the machines in Heinlein's original story. He had some degenerative nerve disease, and he wanted to cure himself by using these tiny robots to operate inside of his nerve cells and so forth. So that's always been on the table, and it's always something that people would like to do. I think you need a lot more than you think you need in order to do that successfully. Because suppose I had a degenerative nerve disease, and I had a machine that could take any atomic configuration and change it into another atomic configuration on the scale of, say, the interior of a bacterium. Do you have any idea how many interiors of a bacterium you'd have to fix all my nerve cells? It's ludicrous. So you're going to have a technology that can not only do that kind of thing on one example of the nerve cell or whatever it is, but do it on literally billions of them at the same time and get them almost all right. And so you're looking at not only nanotech, but a substantial artificial intelligence to drive the thing. Now that's happening. I don't know if this has gotten out yet, but they just did a remarkable experimental surgery a couple of months ago using a robot that was completely autonomous, and it was soft tissue surgery. It was an anastomosis, for those of you who are doctors, at Johns Hopkins. And of course, as an experiment, it was done on a dead pig as opposed to a live human, but it worked. And so that's sort of where you can imagine the state of the art in robotic surgery being. But you have to take that and multiply it by billions working together before you're fixing somebody at the molecular level.
One other technology that could accelerate it, along with quantum computing, 3D printing, nanosurgery, is something you already mentioned, which is AI. One reason you mentioned the date 2029 is because that's when Kurzweil has predicted the AI will pass the Turing test and it'll match human capabilities. Do you see growth in AI suddenly making some of this atomically precise manufacturing or even design of atomic energy systems more likely to happen?
Oh, well, certainly there's going to be an increase in design capabilities. Now, right now, one of the major drawbacks to the way that a lot of the modern AI is done is that it requires a huge volume of previous results. So the language machines that are so, like GPT-3 and so forth, that are so startlingly good, required to have been trained on huge corpuses of actual written language. And right now, we don't have huge corpuses of whatever it is you're going to use to train machines to make completely new stuff at a different level and out of different things that we even currently make them. So it's nowhere near cut and dried that the current techniques are going to be able to do the same kind of thing they've done with language. On the other hand, there's no reason you can't build a physical robot and set it to work and let the AI training program just watch it and see what it does and see what things work and what things don't, and then build, just like the the Heinlein scheme, build 2 of them and then build 4 and then build 8 and so forth. And you get lots and lots of experience that way. So although as far as I know, nobody has tried this yet, it's a possible way of getting enough experience to make a really smart machine in a new field. But again, that's just speculation on my part.
One more possible crossover has been suggested by a comment on YouTube by the McDougall Bugle, who refers to the drone industry. And his comment is that we could easily have had drones delivering Uber Eats and Amazon packages, but regulations are getting in the way there too. However, there's such an interest and a demand for using drones. Do you think this is going to unlock some of the regulations that have been holding up progress? Do you see a connection between drones and flying cars?
Well, I see a definite connection. Right now, the drones are a sweet spot in the technology space. You can build a drone with essentially just 4 moving parts, and there are not that many robots that you can build with that much simplicity. Where the control, basically, what we have is that is cheap, and you get a lot of is computing and control power and the electronics. And so what the drone does as a piece of technology is the part that's expensive, which is the motors and the gears and the wheels and the pulleys and all the physical stuff, has been minimized to just those 4 propellers that are connected to electric motors that don't have any moving part besides the single thing that turns with the propeller bolted onto it, and all the complexity is in the control electronics. Well, that's a really marvelous optimum in the space of designs, and it can do quite a number of things. And the fact that that is true has led people to believe that you could bootstrap from drones to have flying cars and some of the other sort of things. And there's just, you would be amazed how much money is going into battery-powered drone-like flying cars now. And as they say in the book, I don't think it's being all wasted because once we get a power supply that's more reasonable to use with VTOL vehicles, all the rest of the stuff that people have been working with is suddenly just going to become that much more useful. Right now, my travel theory scheme indicates that not having the range is a major drawback for battery-powered flying cars. But as soon as you beat that one way or the other, right? Actually just throw a turbine in it, you get something useful. And in fact, most of the big airplane companies that have tried the flying car stuff have actually gone that route. The ones who actually understand a bit more about the technology of human-sized flying machines. As far as delivery drones, though, are concerned, you're back to that optimum in space, in the design space of flying machines. And there is no reason whatsoever that we shouldn't see more and more delivery drones and drones that do other similar things all the time. And at this point, I think regulation is in fact a major roadblock in that field. How or whether it's going to wind up getting loosened to the point that we really get the full value that we ought to be getting out of drone-like flying machines is something I can't predict.
Fascinating. Time maybe for 1 or 2 quick questions before we wind up the formal part of this event. Then we'll take a short break, bio break, and there is a chance to gather again in a slightly less formal session afterwards, when everybody who's still here will be given the chance to come up on stage as a panelist as well. But let's try and put in 1 or 2 other quick questions. And we've talked about things that might accelerate this change. What about things you could slow it down? PNJ asks about monopolies. whether they are natural monopolies or just companies that have grown very large. Are you afraid of their influence over this kind of innovation, or do you think they could be part of the solution?
Oh, good question. I wish I had a good answer for it. The current way that high-tech companies and so forth works is kind of monopolistic, but generally, like for example, the aircraft industry in the United States, there are a few big companies. If you're building airliners, you're generally Boeing, or if you're in Europe, you're generally Airbus. But there's nothing legally to prevent somebody else from trying to get into it. And especially in the world stage where there are as many different movers as there are, the fact that there's one or two big companies does not seem to have been a major barrier to entry to others. As a matter of fact, I think the worst thing facing the aircraft industry, especially in the United States, is simply what I would call arteriosclerosis in the company. It's what happens to any bureaucratic organization that internally makes it difficult for either common sense or innovation to happen the way it ought to. So I don't really see monopoly per se as a major factor either way in the progress of technology and the technology progress.
Thanks. Let's take one final question from Joy Sue, who just asks, why have so many people been interested in the future of flying cars? And why do people still raise the question of flying cars when the future topic of the future is raised in general? Are they right to do it? Are they acting on a useful intuition, or are they just being pushed and pulled by Hollywood pictures?
Oh, I definitely think it's not Hollywood pictures. Hollywood pictures will take whatever cool ideas out there, and nowadays they'll make cool pictures of them. But the notion of flying cars goes back to the 20s when you had Sierva and the autogyros, and then in America you had Pitcairn, who was, if you looked in the like ladies' day magazines of the 30s, you saw advertisements for Pitcairn autogyros flying you from your country estate to the country club. I mean, this has been around for a long time, and pretty much there were several movies in the 30s that had autogyros in them, but they were following rather than leading the interest, I think. And all of the other kinds. I mean, right now, you know, if suddenly we decided everybody had to have a flying car, the thing we would do would be to get everybody a helicopter. And I will skip lightly over how they're going to, you know, how good of a driver they're going to be, but that's something we know how to build now, and could, if we wanted to, build for everybody. So it's definitely not a fever dream. It's just something that we didn't do, and the question of whether it was something that would have been worth doing is something I tried to treat in the book. And I have my own ideas about it, but it's susceptible of other people's interpretations as well.
So we may come to that in an informal discussion in the pub, as it were, in a moment. I'll give you a chance to offer any final closing thoughts, Josh, but I would like to briefly run through what's happening next in London Futurists. Today we've been talking about your ideas, and to answer a question that Alan Crowley asked, what is the name of the book that we've been mentioning? The book has the same title as today's event, Where is My Flying Car? In 1 week's time, we're going to be looking at the possibilities of risks of human extinction which ones are real, which ones aren't real, how do we distinguish? So we will have Otto from the existential risks community, Otto Barton, and he has set up what he calls an observatory. And we'll look at how do we decide whether the risks of nuclear war or global warming or biological pathogens are serious or not. That's in 1 week's time. In 2 weeks' time, we will look at the results of a survey that took place earlier this year. Some of you kindly gave answers to it. It's a joint survey involving the Millennium Project in the UK, the Fast Future, and London Futurists. There were 199 answers, and this meeting will run through which points had agreement, which parts did not have agreement in the answers, what are the implications, what are the next steps that should be taken. That's in 2 weeks' time. In 3 weeks' time, we will be looking at some ideas in longevity, healthy longevity. How do we get to the state of undoing the damage of aging in our bodies? There's no nanotech on this slide as far as I can see, but there are lots of other therapies, which is part of a hypothesis that these two researchers, Steve Buss and Vincent Giuliano, have called younging. So that's in 3 weeks' time. In 5 weeks' time, we will be looking at a very visionary set of ideas from Elise Bohan, who is a senior research scholar at the Future of Humanity Institute in Oxford, talking about the possibilities that this century will see future superhuman as having transhuman lives, but also, again, some risks of things being badly broken rather than very constructive. And on the subject of catastrophic risks, that was going to be a presentation from somebody at Oxford. Cambridge are hosting a 3-day online conference from the 19th to the 21st of April, in which they look at future risks, real catastrophes, things that have happened in the past, and what we can learn from that, and global solutions. How do we avoid the risks, but without slowing down the truly innovative possibilities, such as we've been talking about in this event? So you can find the details from that website on there, cccr2022.com, or just Google for the Cambridge, the centre, as mentioned there. And yet another talk on existential risks. This is being organised by the US Transhumanist Party, and though they do have 2 speakers from the UK, that's David Pearce and myself. This is taking place tomorrow, Sunday, at 1 p.m. US Pacific time, which will be 8 p.m. UK time, looking at what do we learn and what should we worry about the US-Ukraine conflict from the point of view of nuclear wars or other existential risks. I'm not quite sure what I'm going to be saying there, but it is worth assessing what we might recommend. And that brings us back to today's event. So Josh, thank you so much for bringing some of your ideas to the attention of this audience and for this recording. Is there anything else you'd like to say that people should keep in their minds as they head off for the rest of this weekend?
Well, basically about the book, I was a bit surprised when I recommended it to my friends, and I did not expect people saying, oh, is this going to be too technical for me to read? And perhaps I had gotten a bit of a reputation for that from some of my other books, but the Stripe, the publisher, took my own personal self-published version of it and ran it through the good graces of a very excellent editor, and took out a lot of the rough spots. And by all accounts, it is quite readable for the technically interested average reader. And so I think I can say that you shouldn't have any worries on that score.
I completely agree with that assessment. There are technical parts when you justify what you were saying, but there are very clear expositions at many levels. And so I believe at all levels of reader, especially those who are watching this London Futurist event live or in the recording, will get a great deal of value by engaging with your book. I had some shivers going up and down my spine in various places as I captured the vision of what might be possible not too far into the future, the transformation of cities, the transformation of our life, not just a little bit more of the same, but achieved by working a smaller number of hours, but a much more fundamental uplift in human flourishing. So I have no hesitation in recommending that. And I want to thank you so much, Josh, for giving your time so far. Thank you.
And thank you. It's been a happy to be here. And I will now repair to the back rooms and prepare for the pub session.
Great.
And see you in a couple of minutes.
I'm going to stop the recording, turn off the mic, and I'll be back at about 1/4 to the hour.